So I think we all know Bruno Stuyts, who's going to give us a keynote now.
Thank you, Fraser, and thanks, Sinon, for chairing the session. When we talked about ISFOG late in 2018 and then during 2019, the organizing committee said it would be great to have something about data science. We see it as an up-and-coming field. And then I thought, well, why not just put out an example problem and see how we as geotechnical community perform on such an open prediction event. So we had the pile driving prediction event on Kaggle. I think it was a real success. And now, almost 3 years down the line, I'm here delivering this keynote, which for me is definitely a career highlight. And to be doing it in the presence of Peter, whose tools and company's philosophy have been instrumental in much of my own work with Python, is even more of an honor. So in this keynote, I'll be talking about machine learning and how we as geotechnical engineers would see it and what it can mean for our careers. I'll talk a little bit about data collection for machine learning, because the data collection part, in my mind, is where we can make fairly substantial advances in the upcoming period. I'll talk about model accuracy, and that actually comes back to the question that was asked last, because I think being able to rigorously evaluate machine learning models will increase our confidence in these models. And I'll talk about some metrics which may be specific for our geotechnical data sets. And then for those of you who are entirely unfamiliar with machine learning, I'll just give a short overview of some classification and regression workflows. I think most engineers will use supervised learning to begin with. There's also unsupervised learning, but I've only got 30 minutes for this talk, so bear with me. If we look at the definitions of artificial intelligence and machine learning, these definitions actually demystify a lot of the buzz that there is around these things and how they will eventually replace us and put us out of jobs. Because if you read the definition of artificial intelligence, you can see that conventional computer software, even deterministic software, would fall under that definition. Machine learning is then a subset of artificial intelligence in which we will train a predictive model to make predictions based on data that it gets fed to it. So the system actually learns a certain behavior from the data that it sees. And if you look at those definitions, then almost everything we do on a day-to-day basis with computers is artificial intelligence. And machine learning is also not new to our industry. I think since the start of the geotechnical profession, people have formulated correlations which correlate one geotechnical property to the other, trying to establish the underlying mathematical relation and to optimize the coefficients of that relation. One of the side effects of starting to get into computation and sort of computer-based rules is that you go down a rabbit hole of some very nerdy humor. And I encourage everybody to check out the cartoons of Randall Munroe, aka XKCD. I think as an engineer and a scientist, they're always great fun to watch. But in effect, actually, the machine learning system as a sort of pile of linear algebra which takes in data is sometimes not too far off reality. But if we compare that to our existing workflows in geotechnical engineering, I think our existing practice is also not too different from what we do in machine learning. Because we all start by carefully collecting data on our projects. We do surveys, we do laboratory testing, and we make sure that we get high quality data. And those data sets, especially if you're a project developer and do these projects on a serial basis, are growing over time. As engineers, we will then try to select the input variables, which we call features in machine learning, which have a certain impact on the output, the target in machine learning nomenclature. And sometimes we'll also try to transform what we measure, the raw data, to an engineering feature, a feature which captures what we understand about the physical behavior of our system. We then fit the model to the data, the learning phase, and make predictions for unseen data. So if we're already doing this, well, what's all the fuss about then with machine learning? Well, I think there's a couple of differences. First of all, we have the increased availability of machine learning. So actually, if you look at a library like scikit-learn, you can use machine learning models very easily without actually being a coder, without having to code the underlying mathematics which support those methods. The documentation of those packages gives insight into the mathematics, but you as an engineer can focus on what you need to feed to the model and interpret what comes out. So with those packages also come certain aspects of script-based workflows, automation, and then tools to avoid building black box models to evaluate your models. The advent of offshore wind has also led to increasing amounts of data. I think the data volumes with offshore wind farms are many times higher than what we see, and as that industry is only accelerating, we will see data sets getting even bigger and bigger over time. I think handling data, and especially digital data, in a more effective way has been recognized. So the AGS standard has come out, DIGS standard in the US. And so we are getting better at managing geotechnical data, but we're not quite there yet. Feedback from construction, if you think about hammer logs from pile driving, jacking records from jack-up vessels, all of that construction feedback can come back in digital form, and sometimes it can even come directly from sensors. The first talk by Silicon Lab on the first day talked about IoT and how sensors are directly connected to the internet and immediately feed data to the cloud. Well, that monitoring data leads to ever greater volumes that tell us something about the geotechnical behavior of our structures. And then finally, the computational power has increased. I think for most sort of exploratory machine learning in geotechnics, what you have on your PC is almost sufficient. And if you don't have sufficient computation capacity, it's relatively easy these days to go to a cloud-based machine learning workflow. People often ask me, well, yeah, I'm interested, I want to know more, but how can I get into machine learning? And I've thought about that for a long time because I've had different views. And I'm just trying to formulate a couple of approaches here. This is just my opinion, but I see that there are several engineers out there who will take what I call the full stack approach. They will learn all the tools necessary, they will look at the data, they will process the data themselves and practice. They will find a data set in their company that they want to use machine learning on. And that's a little bit what happened with me and the pile driving data set in the end. And in that full stack approach, you have an individual or a small team of individuals who will internalize all the knowledge and will actually lead the way showing machine learning workflows to others. The comment that I had on this was, well, I'm interested in Python, but I don't have the time to really learn it. Well, okay, I can appreciate that because we're all busy. So I try to formulate what I call the manager's approach. And in the manager's approach, it's really about leveraging the knowledge of a general purpose data scientist who you will engage with and who you will communicate your subject matter expertise to. So at the beginning, you will facilitate the transfer of data to this person, and you will also importantly communicate on how it was collected, because data sets can include a certain bias depending on how they're collected. It's essential when you're working together with a data scientist that you also invest time and effort in that process, because if you just feed the data to the data scientist and say, yeah, just give me a model at the end and then I'll pay you, I don't think you will come to a good result. So you have to engage with them every step of the way, and machine learning workflows are by nature iterative. They will come up with a model, you'll evaluate it, you'll comment on it, they'll come back and do the same thing again until you arrive at something which is acceptable for deployment in your organization. And there are several ways to deploy machine learning workflows. It's not that you have to learn Python or do things in Python. There's many different ways. There is a third approach, and I call that the ostrich approach. And I think as geotechnical engineers, it's acceptable to stick your head in the sand to study its geotechnical behavior, but not when it comes to data science. I think the ostrich approach is just to leave things as they are, to continue with file-based workflows and eventually be overwhelmed by the volume of data that comes in. Model versions is also something where it can go wrong. If you create a spreadsheet, you send it to someone in your organization, you update it later on, but they don't update it. I mean, it's possible to still make spreadsheets work, but it's going to take a lot of time and effort, and there are just better tools such as distributed version control for code out there to do things in a more rigorous way. Data loss is another risk that you have. Data gets saved on a project folder somewhere, project gets archived, people leave the company, new people come in, and you forget that the data even existed. Especially if you have research programs that, for instance, were conducted in the 80s. I mean, we find it hard to dig out the actual data from the papers and have all the context. So the statement where you wait for others to update codes and standards is absolutely not meant to offend the people that put in hard work on codes and standards, but we've heard in the presentation on SafeBuck that there are people there who are just waiting for an equation to plug numbers into, and therefore it's just not a meaningful thing to not read the standard and actually understand all of the underlying research. So I think with the ostrich approach, you can sit back, relax, and wait for someone else to take your job or to be put out of business in the end. Because what we have to realize is that a lot of the knowledge that we've gained over the years is actually residing in our data. The measurements that we've taken during research programs, the surveys that we've done, reflect what we know about the soil. And a lot of that knowledge is sitting inside of our heads. And if we can somehow manage to bring part of that knowledge out explicitly into workflows, machine learning workflows, engineering workflows, we're already doing a better job at preserving knowledge for future generations. So on to the more practical aspects of machine learning. Let's talk about data collection, because in the end, the data collection phase and the data processing phase is going to take a long time. Most of the data scientists' work is actually spent during those phases. And we need to ask a couple of questions, because are we collecting the right kind of data? It's something which we must be conscious of. We must determine features which have the most influence on the output. When you're doing a jackup leg penetration, you may not be very interested in the color of the jackup vessel. But the SpotCan dimensions, I think, are probably a more meaningful feature. Also, the features that explain the observed behavior have to make sense, because we've talked a lot about monopile response analysis and how it's governed by stiffness. If you're only measuring ultimate strength properties, you're not really going to get there. You have to collect those meaningful features. The sufficiency of data depends on geospatial variability. Some sites will be very homogeneous, others will show a lot of variation, and we've got an ongoing task in TC209 to look at this issue. In addition to covering a site geospatially, it's also good to cover the entire parameter space of a problem. If we are doing pile testing, for instance, and formulating models from pile tests, it's nice to have pile diameters in the range for the piles that are actually under consideration for the foundations that we're designing. So covering the parameter space will ultimately determine how successful our machine learning models are in making predictions, because often these models are actually interpolating our data. Extrapolation without an understanding of the physics may be dangerous. And then I think quality of data is something that we luckily as geotechnical engineers are already talking about on a day-to-day basis to reduce the measurement uncertainty. But we have to take into account that certain features, certain measurements will include a certain amount of operator dependence. So we may have to collect certain metadata as who actually was pushing the button at the time of the data collection. In terms of harvesting of data, I think we have to look at making the transition from file-based data storage to databases. And I think databases are not yet adopted in every company, but they have many different advantages. I think they allow you to do the data QA/QC once and then upload the data. I think most of you will know the workflow where you're looking at a PDF report, and every time the engineer does the analysis, he has to sort of eyeball the number from a PDF plot again. So if you do that process once and you do it rigorously, the data is there in your database basically for as long as you need it. We have very good tools to do that, also geospatially enabled databases, so there's no reason not to look at them. And also with unstructured data fields, we can capture different data formats. Certain labs will capture more data on a problem than others. Interaction with the data then can happen through an API, and before this audience I have to say that API in computer science stands for Application Programming Interface and not American Petroleum Institute. I'm sorry, but I think actually the world over, more people will know API as this. And you simply interact with the API by sending it certain web requests and getting the data back as JSON. If you do that, you can build parametric workflows, and there are several ongoing initiatives that employ such a workflow. But I think as a community, we haven't yet settled on like a uniform framework for building such databases. I think the handling of data does require some scripting knowledge, so that may scare some people to go down this workflow and rather work in programs, but I think it, especially for looking at data as a geotechnical engineer, learning a package like Pandas can pay dividends very quickly. Let's have a look at the data sets that were used in the Keynote paper. So there was one for the classification problem, where we tried to predict the soil type from the CPT records. And so we had 16 boreholes with combined CPT and sampling for the Borssele offshore wind farm from RVO. And so we had the CPT readings alongside the sample descriptions, and those sample descriptions were rationalized in soil class according to Robertson's classification. If you look at this plot, which explores the data, this is called a scatter matrix. You can see histograms of the data on the diagonal and on the off-diagonal terms. You can see how the features interact with each other. And you can see that Robertson's chart and the interaction between QT and FR and QT and BQ actually does allow for some differentiation, explaining their rationale. Now, with that data and with that knowledge, can we build a better model for classifying soil types? That was the question. And then if we look at such data, especially if we have pre-existing models, we need to be aware of what we call the narrative fallacy. So we as humans intrinsically have the inclination to make the data confirm what we already thought about it. So we have a certain hypothesis and we say, oh yeah, look, this data sort of confirms the Robertson chart. But actually we have to be a bit more critical. We have to let go of our prior beliefs and check if our hypotheses are really confirmed by data. For regression, we looked at CPT-based pile driving performance. So there were 114 jacket piles driven in the North Sea. This was the subject of the prediction event, and we had CPT profiles, structural dimensions, and driving records at every location. There was also some geospatial data communicated to the participants because maybe they were able to do something with that geospatial structure, although the correlation between locations was limited. The only thing which we did realize was that the blow count did include some operator dependence, so the operator wanted to keep the hammer working at a steady blow count. So actually the blow count was not the best target variable here. If we build a machine learning model, we have to know how to assess its quality. And there we have to make a certain trade-off between the bias of the model and the variance of predictions. And if you look at the plot on the top right, you can see a data set, and that data set does seem to show quite a quadratic variation with some random variations around it. So it seems like the quadratic model is striking a sweet spot there. The linear model is clearly too simple. It's underfitting the data, and a k-nearest neighbor model with 1, which just selects the nearest data point, is clearly overfitting the data. So you really get an oscillating trace, and if you would use that for predictions on unseen data, they would fluctuate a lot as well. So there's a lot of variance depending which training set you use. So getting that accuracy right is important, but what's also important in machine learning is that your model generalizes well. It shouldn't just predict exactly what the data points tell it. It should also perform well on unseen data. And for accuracy, we have a couple of metrics in regression models. I think mean absolute error, mean squared error, you will be familiar with that. And the coefficient of determination explains how well the variance of your input data is explained by the model. In classification, where we try to predict a discrete variable, we could use the accuracy score, but that's just a single metric. It counts the total number of correct predictions over the total number of predictions, so it should be as close to 1 or 100% as possible. Or we could sort of inflate that metric and look at what we call the confusion matrix. Contrary to what the name says, it's actually meant to give you more insight rather than to confuse you. But on the vertical axis, you have the true labels, and on the horizontal axis, the predicted label. And for instance, here you can see that for soil type number 3, the cohesive soils, this linear classifier was predicting that well in 91% of cases. For the clean sands, soil type 6, it was only in 49% of the cases that the model gave the correct prediction. But we saw from the data that it was actually quite hard to make the distinction between sand and silty sand based on the CPT data. In order to check how well the model performs on unseen data, we will partition the data set into different sets. So we'll have a training set that we use to train the model, but we will hold out certain data that the training has not seen to evaluate the performance. And if the model is good, if the model clearly captures some kind of underlying phenomenon, then it will score comparably on the validation and test set which have been held out. In Geotechnics, partitioning data sets may be a bit difficult because our data volumes are not too large, actually. And often, for instance, at the site that we used for pile driving, we had a limited amount of clay layers. And if your training data set does not include clay at all, and your test and validation set does include clay, well, you're going to set yourself up for a problem. So there may have to be a bit of control in that partitioning. Clearly randomized partitioning may not be completely fit for purpose if you have like a small amount of clay layers. Also for model metrics, things like accuracy, there are a couple of comments to make from the geotechnical perspective. If you look at these predictions of blow count, you can see the model predictions as the red dot and the observed trace as the blue line. And what we see is that towards the end, towards the deeper depths, we see that the model is under-predicting the blow count. So you had to hit the pile harder to get it in. For geotechnical engineers, that is obviously worse. This under-prediction is worse than an over-prediction. In capacity problems, it will be the other way around. So the accuracy metric, looking at equal weights of under and over prediction, may have to be adjusted depending on the problem that you have. Also, there may be certain depth ranges in which you're more interested in accuracy. I think typically at shallow penetrations, the piles go in quite easily in sedimentary soil profiles, and you will be more interested towards what happens at the bottom. For partitioning and generalization, in geotechnics, we're dealing with location-based problems many of the times, and partitioning a data set based on location may be meaningful, because if you have a large data set and you split it at random, including 10 points from location A, 20 points from location B, that already introduces some knowledge on each of those locations. So holding out a complete location and making a prediction on a completely unseen profile seems to be meaningful for these depth-dependent problems. In our machine learning workflows for the pile driving prediction event, here are the leaderboards that were ultimately the result of the competition. And you can observe that actually the iterative nature of machine learning workflows becomes very clear. All teams, or most teams, performed several iterations before finally selecting the model which they thought was best for purpose. So we had 61 teams, and 10 of the top 10 teams all had a geotechnical background. So I think data scientists are not going to put it out of work anytime soon. That's good news. And then I would like to have a round of applause for the Fugro Geodata AI team, because they took home the prize. The top scorers were using ensemble models and support vector regression. These are relatively complex models, but what's encouraging is that even a linear model in which the user sort of made meaningful linearizations of a feature still scored pretty high. And actually that gives already a hint for the next slide, in which we can see how translating our geotechnical knowledge into the machine learning workflow will improve things. If you're more interested in the machine learning workflows, the material from the workshop which I gave on Sunday is still up there, so you can check that out. A linear model is quite instructive to use for explaining machine learning modeling, because we're quite familiar with linear models anyway. We try to optimize the coefficients A0 to AN to give the best fit to our data. But this implies that there's a linear relation between input and output. And as we can see from the plots, for instance, QC and blow count do not vary linearly. Cumulative shaft resistance and blow count do not vary linearly. But by transforming that relation, for instance, by including a tangent hyperbolic law, we can linearize and build a meaningful linear model. You can see the predictions in the 3-panel plots, and actually, while not capturing the small variations of the pile driving performance, the linear model struck a reasonable average, and one of the advantages is that you can just investigate its mathematical form. You can improve on linear models by applying a penalty on their coefficients, which we call L1 or L2 regularization. And that process can also highlight which features are of most importance, because if you keep adding on features, you suffer from what we call the curse of dimensionality. And that kind of analysis allows us to extract the most meaningful features, but we have to make sure that they're all working on the same scale, because if QC varies from 0 to 100 megapascal and hammer energy varies from 0 to 4,000 kilojoules, you're not comparing like to like. Deep learning models, you may have heard a lot about artificial neural network and deep learning, and basically they are a model where you construct several hidden layers and assign weights to each of the neurons, and then make a weighted sum and put that through an activation function to predict the output for the next layer. For the prediction event, they were not that successful, and I think that was mainly because we had a relatively small data volume, and also these form black box models, and those black box models have to be interpreted to see if the things that they are predicting are physically meaningful. Because for the deep learning model that was trained for this pile driving dataset, you could see that in general the predictions were a bit poorer than for the linear model. And also for the low cumulative shaft friction, you could see that sort of funny dip happening. The blue is the model predictions. So that seems to be something non-physical. So you have to evaluate your model thoroughly. For classification, I think the decision tree is a useful way to start. In the decision tree, you will ask certain questions about your dataset to partition it at certain nodes, and you will select the question or the split which creates the maximum information gain, and then continue with that process until you reach a zero information gain or a specified maximum tree depth. You can see an example here where consecutive questions are being asked. Here, a tree depth of 4. But if you ask too many questions, if you put the partitioning too fine, you actually get overfitting, and that's illustrated here. The log QT, log FR space is partitioned based on the models, and with a maximum tree depth of 4, you could see that these regions are relatively coherent. But if you increase the maximum tree depth, you might get more accuracy on the training data set, but you get these sort of funny jumps from one category to the other, which are clearly physically non-meaningful. A soil is not going to change from a silt to a sand because its QC changes by 1 MPa. And then finally, ensemble models are models in which you combine predictions from different types of models, different so-called weak learners, and you aggregate them with the underlying philosophy that the errors from the different individual models will tend to average out. These were among the most successful models for the ISFOG competition, and I advise you to check out models like XGBoost or Random Forests. So finishing off, just slightly over time, sorry Fraser, AI and machine learning, I think they're closer to us than we think. It just takes a little extra step to get to know them a bit better and get familiar with them and get confidence. And with the modern data science libraries, you will be able to quickly build machine learning workflows. I think in the workshop, with just a couple of lines of code, we could train a very simple machine learning model and get results back. I think the challenge is upon us to make sure that our data becomes accessible to people. Perhaps certain data sets can be disclosed to the wider community as well, to foster things like open innovation and actually also bringing the knowledge to a broader audience. And then finally, model building is not without risk. We have to know what's under the hood. What it always helps to understand what the mathematical background of machine learning models is, and you need to learn how to evaluate these models carefully. Thanks for listening.